the people that have joined us online. As Shirani said, I'm a PhD candidate at the Department of Atmospheric Sciences. It's a presenting. I'm going to present some of the methods that we usually use and some of the approaches that we usually take when we want to use some of the AI for like either weather problems and climate. But before beginning with this, I want to do like a little icebreaker. So let me share my screen here. It shows. So people can join this link or scan this QR code. I just want like a little or brief description of what is your current relationship with your data or any model that you're using, but only using emojis. So I just want to start like some discussion with these if people are down to it. I may also do the same. That's a pretty good one. Okay. That's it. Does anybody want to make a comment on like what they submitted and why? I mean, I see like school. Oh, okay. Tired. Yeah, I get the feeling. So in my case, I just submitted like this little guide. Everything I do most of the time, it's kind of buggy. Sometimes it works, sometimes it doesn't. So does anybody want to share something here with what they're looking at? And maybe the data set that they use in their research or the model that they have trouble with? Well, I can start for once. The data that I work with is usually on the climate record. I do research on ENSO. Most of the time, this data is not like long enough to actually do some AI methods. And we have to resort to general circulation models or numerical methods or numerical models to kind of fill this gap, which sometimes you get things that are not close to reality, and then everything gets like real bad real fast. Like with these AI methods, one of the key things that you gotta remember is if like messy data comes in, messy data comes out. Okay? Just to not use other words, but that's basically the whole point. Okay, I mean, I guess this is probably a summary of what everybody feels with their work. So I'm just going to start with the presentation. Okay, so going back to this, first we got to define what is weather and what is climate. The main difference between these two terms is just time scale, usually. So here we have a plot where we have like a time scale on the x-axis and the size or the spatial scale in the y-axis. We're going to focus only on the x-axis, and we can see that for weather forecasting, we're usually looking at events that happen within minutes, within days, or within weeks. Something that is actually of interest for many people. It's like, is it going to rain tomorrow? What's going to be the temperature in the next week? Or the temperature that you actually look in the forecast or in the app on your cell phone, that is usually related to weather. If we go a little bit more than that, we enter on the climate scale, which is usually in months, years, decades, longer time scales, and this is associated with different processes also in the atmosphere, like the monsoon, El Niño, decadal oscillations. This is mostly related to if For example, we are going through a drought season, to a rainy season, or things that you don't actually see often, but on average, the average of the weather is what we have as climate. And then if we just go to more than decades and multiple years in general, we have what we call the climate projections on weather on long time scales. So what do we use currently to study all of this? Wait. Okay, so first we have weather and climate models. These models are based on our physical understanding. Somebody has to have actually understood the physics of whatever we want to study. Then, using high-performance computing, we kind of do a numerical method for solving these kind of equations, like physical equations. And this results in what we know as a traditional weather models or numerical prediction, numerical weather prediction in general. So there is one thing, like traditional models consume hundreds of hours of computing power in high-performance infrastructure. So if you want to run a model for multiple years, multiple decades, or hundreds of thousands of years, it is slow and it can become expensive real fast. So what is the other alternative? Instead of physics-based methods, or physics-based modeling, we have data-driven methods. This has been around for way a long time, and it just happens that AI is one of these methods here. So instead of solving the physical equations, we can just model the relationship between the variables that we have. We just compute some weights that we feed to the data, and we have some kind of statistical relations. So the performance of these methods usually depend on the quality of the data that we collect. That's why at the very beginning I said, whatever comes in, the quality of the data that goes in any kind of AI model, because it's a data-driven method, it's the quality of results that you're going to get at the end. So there is a lot of ETL, like transformation, data processing at the very beginning. And you're going to find out that more than 90% of the time you're going to spend just cleaning your data instead of actually developing the architecture. So just as a quick comparison, so we have the traditional models versus the AI models. So traditional models run on CPUs, like on high-performance computers. They have hundreds of CPUs, where AI models can also run on CPUs, but they are accelerated by GPUs, which are graphical processing units. Accessibility is kind of different because not everybody has access to hundreds or even thousands of CPUs on a daily basis. But for AI models, even a laptop like this one that doesn't have a GPU can run some of these. Well, you can build your own AI model for a highly specific task, or you can run even one of the most recent climate emulator, which is something that I'm going to go over in a minute. Regarding cost, there is kind of a balance here because GPUs are not cheap either, but you don't need as many as CPUs. So it's kind of like a balancing. Some will say that it's actually cheaper, some will say that it's actually more expensive because of energy costs, and you can probably tell, like, everybody has been talking how like ChatGPT, it's like consuming energy like crazy every day, and you need cooling power to counteract like the warming, and it becomes crazy expensive sometimes. Yeah. So how does this apply to the topic of the workshop of today? This is the kind of like a summary of the most popular models that we have for weather prediction using AI. Some of the big companies like NVIDIA, Google, and Microsoft have developed like these AI models, or sometimes they're called AI emulators or weather emulators, because they've actually tried to emulate the current state of the climate system or of the weather system. So how does this work? For example, in this case, GraphCast. So you know, when you have a numerical model, you have a physical equation, right? And this equation, it's usually a differential equation, you need some initial conditions to start the system, to jumpstart the system. And then you can have a rollout of the whole system based on what you started the system with. This is the same concept, but instead of solving physical equations, you just have an AI model in the middle. Architectures that they use are pretty insane. We're going to try to replicate some of the results that they do in the coding part of this workshop. Also, as you can probably tell, resolution is pretty high. Time resolution is also pretty high. So this is usually done for up to 15 days ahead for tracking hurricanes, like tracking or forecasting temperature or precipitation or some other variables like that. For example, in this kind of animation here, we can see like the IV tracks, which is like a track of a hurricane here on Y line, and then the Aurora, which is the AI model from Microsoft, has an actual very accurate prediction compared to other methods here. So this is for weather. So what about climate scale? In weather scale, we usually deal with weather station data. Weather stations, we collect data even in minutes, hourly, daily. You have high frequency data. But on climate scale, you usually don't have that. In my particular case, the research that I do is on El Nino. So I'm just going to be introducing what El Nino is, because we're going to do some coding in the coding part of this workshop to do ENSO prediction, or the phase of ENSO prediction as a part of the example. So El Nino, as I already mentioned, it's a large-scale natural shift in the tropical Pacific climate. So it happens on very long time scales. Usually between 2 and 7 years. It's regular. It's a non-linear, highly non-linear process in general, and it's perfect as an AI example because what AI methods excel in, it's trying to solve non-linear problems. You always have to use a baseline, so use a linear model as a baseline for any kind of application that you want to make, so you can actually see if there is any improvement or not. Because most of the time, even as fancy as it sounds, AI is not always needed. Like sometimes the most basic linear regression can get the job done. So for this particular case, what are we going to do, or how do we actually study El Nino? Is the whole map of sea surface temperature that we have on the Pacific. We just take an average on the box in the Central Pacific, and that is what we call the ONI, or Oceanic Nino Index. This is like a summary of what is the state of El Nino in the Pacific Ocean. And as you can probably tell, this is a time series. If we're dealing with time series, we can do some time series forecasting. And this is actually a good application for some of the AI models that have recurrence. Why is this important? Well, this is just to show why we do research on El Nino. It has effects all around the world. You have weather-warm conditions. When it happens, you have weather-warm conditions over the Eastern Pacific. You have dry conditions here, including Hawaii, which is actually, this was the conditions when the fires happened, like in 2023. Just to get some sense of the work that we are doing here at UH using AI, this is some published research that we do to forecast or try to understand how El Nino develops on the Eastern Pacific, and not only use AI models to do that, but actually try to explain, because most of the time, probably everybody is familiar with this, they've heard that AI is treated as a black box. Like you cannot get any information of what the model is doing. There are actually some methods, and this particular branch of AI, it's called explainable AI, which is something that not everybody is speaking on. If you manage to apply it to a particular problem, you can extract where the model is actually looking at in your input maps. Some other application, but using climate emulators or weather emulators in this case, it's using this delisting AI model, which is also a work done by another group member. So they were actually looking at the blockings here, which is part of the atmospheric process. But the whole point is that these climate emulators, or this AI method, can capture major characteristics of atmospheric or climate variability that we know. So it was just a general introduction. I just went over most of the stuff very quick. Now we can just go in the code and go into the hands-on part of this workshop. We're gonna do, everybody feel free to scan this or go to the link. They are gonna be met with this. Oh yeah, okay. Okay, so these are the notebooks, the code that I prepared for this part of the workshop. We're gonna try to do 3 main parts in this whole session. The first part is we're gonna try to tackle some weather station data. We know that's high frequency, we have multiple variables, we have a lot of missing values. Most reliable sources are airports. Airports have weather station data. You can pick whatever airport you want. In this case, I picked like San Francisco airport because it's more reliable. I tried with Honolulu, but there are some caveats there. The second part is going to go over the climate aspect of this workshop. We want to try to do the ENSO-phase prediction using maps as a surface temperature. And the last part, we're going to do some weather foundation model. This is like the current state-of-the-art models that, in this case, we're going to go over the Prithvi model, which is developed by NASA. A weather foundational model, it's basically an AI model that has been trained with petabytes of data that you can take and you can just use for whatever purpose you have. You can use it for like energy, you can use it for hurricanes, you can use it for basically the options are unlimited. So once you are here, there are multiple ways that I instructed here how to run all of this part of the workshop. You can use Google Colab. It's gonna be easier because you don't have to set up anything on your computer. But on some of the notebooks, we are extracting and saving some data, which you will have to download and upload multiple times between the notebooks, so you can have everything working like seamlessly. If you prefer to have it locally, there are also some instructions on how to do it. If you have Conda installed on your computer or Mamba, you can just run this set of commands and everything is going to be ready for to work. Or if you are a little more advanced, you can use Docker. Right, everything is already in a container, so you just need to download this if you have Docker installed on your computer, and then do Docker Compose app, and you have your Jupyter Lab session ready. Okay, so I'm gonna run. So for people who have tried to run this using Jupyter on their computer, they should be left with this. Otherwise, you can use also Google Colab, and if you have any problems running it, just let me know. Okay, this looks good like it. Okay, for some reason it's not working, so I just must. I'm gonna do Google Colab too here. So the first part, we're gonna try to do some. Oh no, come on. Okay. Yeah, you gotta be signing for it to work. So we're gonna just follow along. This first part is just gonna be the data ingestion, just to show how like the general overview of this looks like. You get met with this, just run. There is no need to choose or to change the runtime here, as I indicated here in this part, because we're not going to use any GPU for this first part, which is just getting the data that we want to work with. Okay. Okay, so this works. So to extract the station data, there are multiple ways to get workstation data. The easiest one that I found is using a package called Meteostat, which is already aggregates everything. You just put a pair of latitude and longitude points here, or a pair of latitude and longitude, and it's gonna try to find all the weather stations that are close to this point. So these are the stations that I have close to the point that I selected there. We can just keep going on this. In this case, I'm interested in the San Francisco airport data. So that's it. We're going to get all the data that we come from 2022 to 2026. And as you can see, we have 36,000 hourly records of all these variables, like temperature, relative humidity, precipitation, wind direction, wind speed, or pressure here. We can do just some pandas exploration to see how many null values we have, or no null in general. Or we could just describe the data to. This is just some sanity checks to know what we are dealing with. It's also useful to do some plotting. In this case, this is just a heat map of the data we're missing. For some variables, there are 3 variables that basically are unusable because this station does not record them. Some of them, like for precipitation, you have some gaps. Some of them are pretty complete. So kind of just keep looking. This is just a distribution. Oh, sorry about this. Okay. This is just a distribution of our variables like temperature, relative humidity, wind speed, and pressure. And this is going to be like the 4 variables that we're mostly going to use for the next part of this. So you can tell that it's pretty high frequency. There are a lot of variability. You have the diurnal variability here. You have also some seasonal variability because we are looking at 4 years worth of data. The last part, this is just so we can get a data set. So if you're using Google Colab, like me, this data is saved here. So you should try to download it to use it on the next notebook. So yeah, I already downloaded it. Or we can just go straight to the next one. If anybody's there or anybody has any problem with that, just let me know. Because for this part, we're going to explore 3 different strategies to try to forecast the next 12 hours of temperature using only 24 hours of history. This is a classic time series forecasting problem. We're going to explore a linear regression method, which is going to be our baseline. It is fast, it is interpretable, it's a classic linear regression, you can never go wrong with that. Then we have the multi-layer perceptron, which is just the most basic AI method that we have. I'm going to go explain a little bit about this later. It can actually learn some nonlinear pattern matching, but the cons is that it's going to treat the history as a flat vector, as if it were just a series of numbers that don't have temporal correlation at all. And then there are some other particular types of architectures, like the LSTMs or the low short-term memory, which actually have some temporal correlation, some temporal sense. So these kind of networks have been designed for time series, so you can actually understand the long-term dependencies in the data. But it can be slower to train. So we're going to go over all of these. First, we need to run the first. For this one, it might be ideal to change the runtime to use a GPU here. And then just run this. What this is loading, if you have downloaded the data from before, just try to create a folder from data. I don't know when I get it. So you can just create a new folder here. So data, and then drag and drop the file that you downloaded before, that you processed before. So if you're using Google Colab, be sure that if you do this, try to copy the path, because it's gonna depend on this, and then just change the data path. So yeah, we have loaded over 36,000 points of data. This is just some like the initial or the input features. This is all the initial configuration that we are gonna do here. We have these 4 variables: temperature, humidity, pressure, and wind speed. So this is a list where we have all the variables. We can just turn off or turn on any of these as we want just by commenting it. I'm gonna run with everything, so we're gonna have these 4 variables as input, and then we're gonna try to target temperature, because that's what we're gonna forecast. History, we're gonna take the last 24 hours of temperature, which is the last day, and we're gonna try to forecast the next 12 hours. So if you wanna play around with this, just pick these values. Let's say you wanna just forecast the next hour, or if you wanna forecast, I don't know, the next 3 days, or if you want to increase the history for a model and see how it performs with different history. Sometimes more is not better, so you can play around with this and see how all the models perform in general. So one of the important things to do before trying to use any AI method is data splitting. So you gotta split your data in 3 different sets, if possible. And these sets are seen here. A train set, which is what the model is actually gonna see. You're gonna be training against this data, trying to optimize the model to get to the minimum error based only on this data. The validation data set, it's gonna be what the model is gonna benchmark against after every training loop. Because this is gonna, the loss, so on any of these models, whenever you train it, you have a loss function. The loss function is just gonna measure the error of the prediction versus the actual value. If you're using the training set, every epoch of every loop of training, this error is gonna go down and keep going down until you basically overfit. Because the model is gonna try to do a perfect prediction on this. So instead of evaluating the model against this set, you have a validation data set that you run it against. Once this metric, or once the validation or the error on the validation set stops improving, you can hold the training. This technique is called early stopping. And it's something that we are also implementing here in this code. Because there are a lot of hyperparameters you can define in any AI model, and these hyperparameters are just values that the researcher thought it was like the most suitable for the problem they were looking at. So the number of epochs or the number of loops that the model is going to go over for training, it's also a hyperparameter. And early stopping can help us kind of mitigate the issue. If you define 200 epochs for training, but the model stops improving after the 50 epoch or the 40 epoch, this method actually helps the training and restores the best weights. So that is the whole logic of why we have this. This is just a standard procedure we have to use to scale our data because we're dealing with multiple variables. All the variables have different scales. So everything has to be with zero mean and univariance if possible. So yeah, this is basically just boilerplate code that you can find anywhere. This part is one of the most important. We're using PyTorch here. PyTorch is AI framework in Python. You have also TensorFlow and Keras, which sometimes can be easier, but PyTorch is more transparent. Like you can actually see what you're doing. You can actually control everything. With Keras, most of the time they use. I mean, it's not bad. You can also tweak everything, but most of the time they assume that you want to use some kind of specific initializations, which might be good too. But if you want to be transparent, and the one that is mostly used for research is also PyTorch in general. So here we're just defining that data set. This is where we are going to put our data. So I don't think it's worth going. If anybody has any particular questions about this, this is a Python class. All of this is in the documentation of PyTorch, how to define this, and also I think, yeah, I mean, if anybody has specific questions about this, I can just go over the details and try to explain what these are called Dunder methods mean. But we can just go over here and just keep training. So here we define the input length, which are our history hours, the output length, which is going to be the forecast hours that we want. The batch size is how many batches of data or samples the model is going to see at once in one single loop. In this case, the batch size is 64, so we have 64 batches. The model is training batches of 64 at a time. It is good practice. This is also a hyperparameter that you gotta tweak. If you put lower values, you might get better results. If you use higher values, you might also get better results. The only The only way to know is to actually try different values. That's basically the definition of a hyperparameter. That's why most of these methods, when you actually do this for research and want to publish it, you define a hyperparameter space. And this hyperparameter space, you basically do multiple iterations of the same model with different values, and to see which one of these values is the most optimal for the problem that you have. And there are multiple methods to actually do this thing. So, okay, we're just gonna run this with the data loaders. It is also good practice to shuffle that trained data set. In this case, we already have our samples, so we have 24 samples attached with the next 4 samples. That is gonna be our output. And we can just shuffle these samples around. But it's a good practice because we don't want the model in general to learn any kind of like sequential correlation between our input dataset or our input features. This is the training loop. I'm helping myself here with PyTorch lighting, which is a really nice model that plugs into PyTorch. So any kind of this model, you have a forward pass, you have that training step. In each training step, you evaluate your loss function according to a criterion that you define. In this case, since we are trying to predict actual values, we are dealing with a regression problem. So for a regression problem, the usually loss or error function that you use, it's a mean square error. Yeah, this is a validation step where we are gonna use the validation loss to actually monitor the performance of the model. And then the optimizer. The optimizer is another hyperparameter also. The learning rate is another hyperparameter. You see there are a lot of things that can change the performance of your model. So this is just a convenience function to train the model. I try to collect most of the boilerplate code in a single place. So this is where we define the early stopping that I mentioned previously. What we're going to monitor is the validation loss. And the patience is how many epochs we are gonna wait until we halt the process. If the model has not stopped, it has not improved for 5 epochs, then we can just assume it's not going to improve, and then we just cut it. This is a parameter that you can tweak also. I just put 5 here just to have some, just not wait that much. You know. Yeah.
So like a burn-in period? Is that like a burn-in period where, like, if there's something wrong with the data, the model's not working, and you want it to stop, or?
So this is it's like a waiting period for every epoch. Yeah. If the model improves, you're gonna see less error, right? So it's gonna start counting until 5 epochs later. If on those 5 epochs the model has not achieved lower error, then it halts the process. It finishes. Yeah, it stops the training. So that's something you gotta have into account. Sometimes models can take, when you train a model, at the very beginning you can see the error increasing exponentially, and then after one point it just decreases. So that's also one of the drawbacks of this implementation, is that you gotta be aware of the data that you are trying to train on. It might take a long time for the model to actually capture the whole details and lower the error. Yeah, in this case we are not bothering with a lot of patience here. We're just having like, you can also change how many epochs do you want to wait in between checks. So right now we are checking every 5 epochs like very continuously. We can probably say like, yeah, we have a patience of 5 epochs, but we want an interval of 10 between them. So you actually wait for 50 epochs in total until it decides if it should be stopped or not. And that gives you more like legroom for the model. That gives the model more legroom to actually improve. So yeah, up to this point it was mostly boilerplate code, as you're gonna find almost everywhere. So the first one is, or first model that we're gonna evaluate here is just a linear regression. This is just a simple linear regression. Everybody knows this. It's just y equals, well, in this case, it's theta 1, 2x or mx plus b. And the way we can do this is there is something called a linear layer in PyTorch. Even though we're using PyTorch to do the linear method, we are not actually using any non-linearity. What that means, or what's the meaning of that, we're gonna see in a moment when we do the multi-layer perceptron. So we can just run this. You can see there are a total of 1.2k parameters that you're gonna train for. And this is the training loop basically. It's going, each epoch goes over the whole data set that we have at the very beginning. We can monitor the train loss here that it's decreasing and the validation loss, but it might be decreasing, it might not be decreasing in this case. I think here it's going to decrease until, okay, taking a while. But yeah, until that finishes, we're going to go over what is a multi-layer perceptron. So the multi-layer perceptron, this is just the first and the easiest, or I would say the most basic kind of AI method that we can use, or machine learning model. We have different layers. In this case, the most basic, or the basic one, has 3 layers. One input, one output, and in between one hidden layer. So every neuron here, like represented by these circles, it's connected to each other. And each one of these lines is actually a linear regression. So everything that you see on this AI method, at least until up to this point, is just linear regression. So what's the difference between multi-layer perceptron and a multiple linear regression, or just a fancy linear regression, is that these models have something that it's called non-linearity or non-linear activations. So this is applied after the regression that happens here. So each one of these neurons have something called, I didn't include any plot here, but let me see if this finished. This is the, we can do something like this. Wait, we just finished. Okay, for some reason it's not showing here, but this is a nonlinear activation function here. So this one is for every positive value that you have, it returns the same value, and for any negative value that you have as an input, you have 0. And this is just an easy, very basic nonlinearity. So as you can probably tell by all the acronyms here, there are multiple nonlinearities that you can choose, and that's also part of the design of the architecture that you are using. You can consider another hyperparameter in general. Yeah. Here it is implemented here. After the first linear layer, we have a ReLU, which is a nonlinear activation function. We have a dropout layer, which is a regularization. What this means is like you don't want to overfit. So the way to do that is regularization. And one of the methods of regularization, in this case, and the most basic one too, is dropout. This number here, it's the probability, in this case 20% chance of turning off one neuron during the training process. So if we look at all these neurons, each one of these has a 20% chance to be turned off during the training. So that forces the model to stop any training of this neuron for that epoch and force the other neurons to specialize on something else. that's kind of the logic behind these regularization methods. You can keep adding more linear layers. That's going to make the model wide. We usually don't want that. So we can just run this and then see the result later. It's probably going to also take a while, so I'll just go ahead and run everything if possible, because it's going to take a while. So, okay, so the multilayer perceptron takes all the inputs of vectors. They have no correlation at all. They are just numbers in a single mathematical construct. Each one of them go up to different mathematical functions, and then you have your output. The other method that we want to look at was LSTM, so long short-term memory. This looks more complex compared to the other methods we see. It's actually for every input that you have two different additional inputs that are within the model. Which one is called the hidden state, and the other one is called the memory. The memory are the values that the model is actually holding. And how this works, on the inside you have different gates. You have forget gate, input gate, and output gate. There are multiple things happening here. You have sigmoid activation functions, you have hyperbolic tangent activation functions. The whole point of this is that this single cell or architecture is gonna try to find if any value that you are inputting here, it's gonna contribute to the forecast of the next value. And if it's gonna work like that, it's gonna save it here on the memory. It looks kind of like a complex flowchart, but it's actually easier than it looks. So if there's some brief description here, these are the gates. So these gates are going to regularize the flow of information here. The way to do it in code, it's kind of like this. This is just the LSTM. We can also concatenate multiple of these. As you can probably tell, since the architecture is not as straightforward as the multi-layer perceptron, the main issue that these models has is an increased complexity during training. So it's going to take way longer to train compared to the other methods. So right now it is training, so I'm going to wait. One interesting thing about this is, for example, for the we can see the number of parameters or trainable parameters that we have for the multi-layer perceptron. It's 8.7K, and for the LSTM model we have 32K. So if you keep increasing complexity, you keep increasing the number of parameters, you keep increasing computation time, because the model has to adjust for all of these parameters and have to try to optimize every single one of them. Mathematically, you gotta compute do the backward propagation and compute some gradients for each one of these parameters. So yeah, we just gotta wait for this to finish, and then we can just have here a model comparison plot. It's also boilerplate code to have it. So, oh yeah, and well, in this case, what we have here, this is all the history that went in the model. The black line is the truth, the future, and these three lines are the predictions. So in this case, we can see that the LSTM can barely outperform the linear method, but just like a few values. It's almost negligible. Both are like very close. You can keep changing this number here, IBX, if you want to see different times and see how well they have performed in different points or with different samples. So one thing that I wanted to show here is, for example, sometimes, and this is one clear example, using one of these AI methods to try to forecast a time series of a signal that is highly predictable might not be the best choice. So what happens here is you have a pretty much predictable diurnal cycle of temperature, because if you have probably what the linear model is looking at, if you have this decreasing trend, it's probably going to keep decreasing. It's nothing much that we have to look at. So we can try to increase complexity here. We just go at the very beginning, and you can keep trying this also to see what results you have or you get. Right now we're using temperature also as an input to predict temperature. And what about we just turn this off? And we try to predict temperature just using pressure, humidity, and wind speed. That's going to change things. Probably the linear method might not be better, or might not be the best one in this case. We can just keep turning off this and see how it changes, or we can just change the target feature and try to predict a different variable here instead of temperature. But since that is going to take a lot of time, I'm just going to leave it there. And if anybody has any particular questions for this notebook, or is everything going?
Never tried transformer instead of the database old version of the rest.
A transformer, you said? Yeah, I mean, we can even use a graph neural network or transformer. Yeah, this is just an example of like, because if we want to define a transformer, the architecture is going to look a little bit more convoluted than this. In the next part, we're going to try to do a unit, and the code for the unit actually looks a little bit insane. So I just try to keep LSTM for simplicity, and because it's like when you start trying to do time series forecasting, you start learning about recurrent neural networks, like networks that have time information, and then LSTM is just the most popular in that regard. So it was just a choice. Definitely, a transformer might have like a better performance in general.
These examples you ran of the models, they didn't take all the epochs because they stopped when they reached the best.
Yeah.
When the error stopped improving.
So you can see here. Let me show you. So for example, the linear method stop at like 26 of 49. Then this other one, the multilayer perceptron, stop at 19 of 49 too. Everything was set up for 50 epochs, but LSTM also stopped like at 14, like pretty early. If we could give this a little more time, who knows, it probably can learn like most of the nonlinear relationships and can actually outperform the linear method. But just for sake of simplicity and time, we just see how this is performing. Okay, cool. Can go. So the next part is going to be for ends of prediction. We're going to actually deal with monthly values instead of hourly values of temperature. And this is going to be temperature around the globe. So if anybody can run this on their local computers, might be a little bit faster. Let me open it locally. the data exploration is going to consist of ERSST version 6, which is a consolidated data set of sea surface temperature, monthly values of sea surface temperature on a 2x2 grid, monthly from 8050 to the present. We have SST and also sea surface temperature, which is SST, and sea surface temperature anomaly relative to that climatology. So try to run this fast. It's gonna take some time to download the files. Those are like around 900 files in total, 912. And I don't think the most recent value has been posted yet. Yeah, so yeah, 2026 hasn't been posted yet. So yeah, it takes some time for this data to be updated. For this, since we are dealing with netcdf data, very useful package in Python to deal with this, it's called xarray. So we can open all of the data that we have here in a single line. So to give a sense of the amount of data that we're reading here, this 900 file has been opened with this single line in Python. So very useful. Definitely if you deal with geospatial data or climate data in general, give xarray a try. Okay, so we're just going to take the last value and see how it looks. So we have the sea surface temperature, as you can see. Well, probably this color bar is not doing it any justice. But yeah, we can see the anomalies. Right now we have, it was December 2025. We have kind of like a weak cold conditions. An anomaly is just a deviation from the standard, from the what is usual, what we call the climatology. So here what we're interested in looking at is the actual anomaly. This is just some plotting to see like the global mean sea surface temperature. It's area weighted because all the latitudes don't have the same size. And you can see there is a clear trend of how the temperature has been increasing in the oceans over time. We're going to go over the ENSO region, what I explained at the very beginning in the presentation. We are interested in looking at this location. It's called El Niño 3.4. So we're just going to take an average of this. We're going to summarize all these, all the temperature of the tropical Pacific, like this. And we have some set threshold. These have already been defined by NOAA. So we have, if this value is above 0.5, we have El Niño. If it's below,
sorry, I just had a quick naive question, but how is the global average calculated?
So the global average, so each grid cell has a weight that is based on the cosine of the latitude that they belong to. Because on this particular projection, we have the poles that are very...
So there might not be an actual data point for everything, there could be some interpolation between stations or something like that?
So you mean in this case, like is there any interpolation like between grid cells?
Yeah, between like actual weather stations that are collecting temperature data, or is it like,
how
every cell have like temperature data?
So this is a gridded product, so every cell has data. It's because the ERSST is a reconstruction of sea surface temperature. So it takes all the actual observed values and then try to reconstruct using some optimal interpolation methods to actually have the most accurate. It has multiple revisions. This is a 6th revision. So if you compare it with the previous one, you can probably see like on places that you know there are no like records, this data is not like as reliable as in the satellite record. So yeah. So yeah, this is just a basic what we done before, and we are just gonna save. What is this telling me? Oh yeah. Okay, we can just In my case, it gave an error because it says permission denied, but the data exists. So I'm just gonna double check. Yeah, I have it here. It says 24 seconds ago. Okay, yeah, that worked. Okay, this is just the first part of like any problem that we gotta deal with, and we wanna apply AI. We just gotta be familiar with what we are doing. So what we did here was we took the sea surface temperature maps and we summarized everything into a single time series. That this is what we're going to use for next part of answer prediction here. So these are the three different phases of ENSO. What is ENSO? ENSO is El Niño Southern Oscillation. We have normal conditions, so we have like stable winds blowing from east to west along the equator. This is what we call the warm pool. This is what we call the cold zone. And we have this normal circulation. When El Niño happens, this circulation weakens. So we have an intrusion of warm waters towards the east, but it's usually cold. So this brings, or this disturbs the atmosphere in general, brings a lot of, well, it affects not only the Pacific, but different parts, because it's like a wave. But you can probably see here, you have this big convection happening here in the atmosphere, so it's like a wave that it spreads all around the world, creating different effects, which it's known as teleconnections in the atmospheric science field. And you have La Niña conditions, which is the opposite. When the winds are way stronger, you have way cold conditions, colder conditions here, warm conditions, or not so warm conditions on the Western Pacific. So we just need to know that these are the three phases. And these three phases operationally are defined by the values of the ONI, which is Oceanic El Niño Index, which is the value that we have computed before. So compared to the first problem that we had using weather station data, the weather station data problem was a regression problem, because what we actually tried to do here was forecast the actual value of temperature here. Here, on this second part, we are not interested in the actual value of temperature, but we are interested if it belongs, if it's above, if it's below, or if it's within some threshold. So this is a classification problem, because we are not dealing with numerical values, but we're dealing with different classes. So given the last 12 values of 12 months of ONI, we want to predict the ENSO class for the next 3 months in advance. So it's a sequence, basically kind of a sequence to sequence, but in this case for a classification problem. So we're just gonna run like all the boilerplate here, like the import and stuff. We can load the data. We can see all the record that we have. We're cropping it at this point. This is the ONI. It's similar to the one that we saw here. So the main difference between El Niño 3.4 index, which is just the mean, and the ONI is that we just apply a rolling mean. Oh, sorry. We apply a rolling mean that it can be seen here. We apply a rolling mean of 3 months, and we just take the mean, and that's how the ONI, because you can want to smooth a little bit. You want to smooth out a little bit the time series. And this is what we have. As you can see, right now we are kind of on La Niña conditions, because we are dealing, or we are approaching this blue zone below the threshold. So we're going to label everything. It's as easy as just doing this. This is mostly pandas, X-ray magic happening here, if you want to call it like that. To have an idea of how our classes are distributed here, we have 400 months, or about 400 months, 44% of the data is classified as neutral. We have 90% of El Niño, we have 30% 36% of La Nina, which is kind of interesting too, because the most impactful events are El Nino, and this kind of shows a little bit of the asymmetry within these two different phases. La Nina tends to occur for longer periods of time, but it's not as strong as El Nino. You can probably see these huge peaks compared to these ones that are more like wider in general. Same as before, we just defined our data set that we want to use. This is the sequence length. We can change if we don't want to use 12 months. So I try to put everything here in a way that anybody can modify it and just try different strategies. Let's say if I want to have like 2 years worth of data or just the last 6 months and see how the model changes. So most of these decisions are based on the actual person doing the research, what they think is appropriate for the problem they are trying to solve. So for this particular example, I say like 1 year worth of data, it's enough history to actually try to forecast the next 3 months of data. And yeah, we're going to go over the models here. So we're going to go also over a linear model again, which is going to be our baseline. We are also going to do a multi-layer perceptron, which is the one that we saw before. And this time we are introducing a convolutional neural network in 1 dimension. What is a convolutional neural network? Hold on, let me run all these things. So here, the convolutional neural network is basically kind of like a rolling window. In 1 dimension, it's just a rolling window that is going to perform some operation. Like this window is just a set of weights that is going to be multiplied, or it's going to be multiplying all these values and then aggregating them over a new vector series. You can see this is running. We're going to go over the 2-dimensional convolutional neural network, which are the most popular ones used for image classification or image-related tasks. But in this case, if we are just doing basically also time series of ONI values, we want to get the output. Also a 1-dimensional value, we are just going to do the 1-dimensional convolutional neural network in this case. Takes a little bit longer to train to, and we're going to see the results in a minute. Okay, so how does our models perform? Let me close this. So I just drew this line, like below this 32%, basically the model is predicting randomly. It's not skillful enough. Linear model does pretty good in general, but it's clearly outperformed by the multi-layer perceptron and the convolutional neural network. This is one of the problems that you can see, like El Nino has some intrinsic non-linearity. These methods are able to capture this kind of thing. See, with 1 month lead time, a multi-layer perceptron and a convolutional neural network has around 90% accuracy, and it doesn't drop that much with 3-month lead time. So here, this is just the confusion matrices for the multi-layer perceptron. This is one of the metrics that you usually want to evaluate when you are dealing with classification problems. You have your predicted label on the x-axis and the true label on the y-axis, and see how many positives, false positives, or the accuracy, the recall, and all these parameters that you can get, or all these metrics that you can get from these plots. We can also try to do like with the most recent values up to 2025, and see like for December it predicted La Nina, for January also La Nina, and for February it says neutral. And if we go and see the actual values, and this may be running. But we see they only have until December, but it's also about right what the model said, like it's 84% that we are on La Nina conditions, and it kind of checks out. So what happens in the next few months? well, I mean, we're still on, as you probably saw on the initial plots of the data exploration part. We are still on cold conditions. Oh wait, this is 12. But yeah, take my word for it. It's still cold. Yeah. So, well, this is some like key discussion of what we found here. ONI, it's a good feature. It's kind of, if you will, you can call this like a feature engineering of some sort, because we are not giving the raw SST values, but we are actually computing an index from this, and we are using this index to increase the performance of our model. So it's kind of like we are transforming the data in a sense. So now I want to go over the case that I just commented. What if we didn't do that? What if instead of just computing the ONI, we just give us an input, the SST, like the actual map of sea surface temperature. So we are inputting images, and the output is going to be the same in your class. This is probably reversed from 2D to 1D. Yeah. So again, this is just boilerplate to define what are we going to deal with. What are we dealing with here? We're going to do a convolutional neural network classifier. This is where usually the convolutional neural network shines. It is mostly for object detection, not in this particular field of climate. But as you can see, you have different layers, like a convolutional layer, you have your input, a convolutional layer here, you have a pooling. A pooling refers to you aggregate values and you try to reduce the dimensions, because what you want to get at the very end is just a summary of all the data that has come, like all the input data has to be summarized into multiple different matrices. And then at the end, you have these what we call like the fully connected layers, which are, this is basically a multi-layer perceptron at the very end of the convolutional networks, of the convolutional layers in general. But it's kind of like a mix between the two. And how does convolution works in 2 dimensions? It is like this. So for any input image that we give, this 3x3 filter is going to go over the whole image or the whole grid, and it's going to try to summarize or aggregate the values into a single grid cell. And that is what's happening here in this classifier. So yeah, this is a code. As you can see, it is getting, each time we try to do something here, it gets a little bit longer because we're doing convolution here, the nonlinear activation. And as we go down in the network, we can keep increasing the number of kernels or the number of filters, in this case it's called filters, until we get to the flattened part, which is where you get the fully connected layers, which is defined here. And this is basically the multi-layer perceptron that we did like on the weather station data part. Okay, so this constraint. To compare it with another network, I tried to adapt a UNet. This is the most popular network for multiple tasks, and also the most complex one that I'm gonna try to explain today. It's basically composed of multiple convolutional blocks. Each one of these is a convolutional block. If you will, you can understand that each one of these is a convolutional neural network layer, like this one that we saw here, but encapsulated not as a full network, but as a component of a bigger network. That's what usually happens here. And what is called a UNet, because on this branch, which is usually called the encoder part, you keep reducing dimensionality, like going down, increasing the number of layers, until you get basically a vector here, which is called the latent space. This latent space is able to summarize basically your whole input or training data set that you use here. After you have your latent space, from this vector you're going to start reconstructing back your figure, your image, or the map. But it doesn't stop there. What's the whole point of the unit is that on the reconstruction side, you actually also take as input one of the you take as an input one of the matrices that you get when you are going down in the encoder, and this is represented by this line. So as you keep going down and summarizing everything, you will think that you are losing some information. And when you go up, you actually copy one of the layers here and concatenate it back here. So you are not losing information, but you are gaining information in different scales. Like this one, it's actually looking at fine details. When you reduce dimensionality here, you start trying to look at more broad details. And the lower in resolution you go, the broad the characteristics that the model is able to capture. So that's kind of the logic here in a unit. And it has this U shape. And the actual name of these lines that go back and forth between these two different parts are like a residual connection or skip connection, it's what they call. So yeah, the code for that, it's a little bit long here. But yeah, this is the first part of the encoder, as I'm showing here in the code, then the bottleneck, and then when we go up, we actually concatenate as we go up with the results that we got previously from going down in the encoder. So in theory, these methods are suited for 2D inputs, like image input and image outputs in general. It is not suited for this application as it is, because for weather and climate, you have different things that you gotta account for. Most of the things have to deal with seasonalities or positional embeddings, or depending on where you are on the Earth, everything changes. So I'm just going to go over this real quick and see how these two compare. And yeah, as you can probably tell by now, the more complex or more complexity we add to these models, the longer it takes to train. So early stopping is actually a good technique, because you don't want to wait an hour for a result that might not be ideal when the model have actually improved, like after the first few 20 or so epochs. In this case, I highly doubt that it's going to be better, because we're giving the model too much noise. We're giving the model the whole map of sea surface temperature instead of doing feature engineering like we did with the ONI. We give the model the data that we know. Like as humans, we actually want to look at these indexes instead of looking at the raw map. So we gotta treat this the same. So they, unless you want to go complex enough or high complexity enough, you're not probably going to get much if you just give the data as it is to the models in general. So yeah, this is taking a while. I'm just going to run the whole notebook then. Is there any particular question up to this point?
You said it's an image input and an image output.
Yes.
Is the output going to be like a map of the classifications, or?
In this case, what I did is I kind of brute force it to be one-dimensional output. So you can customize this however you want. So what I did here at the very end is I basically did a global pooling. I kind of chunked everything together and then try to create a vector. So it is not suited for this. Right? The next example after this one, it goes over creating the next month sea surface temperature map. So this one tries to actually create a map. But yeah, it's gonna take a little bit. And before we run out of time, I'm probably gonna go over the last part, which is gonna be pretty quick. This one, I do really recommend using Google Colab in this one, because if you don't have a GPU available in your computer, it's gonna run, but it's gonna take a lot of time. Oh, this one already finished, I think. Yeah, we can probably see. We can see here, it's like the convolution on the two-dimensional and the unit, they have not increased skill whatsoever compared to the previous method where we actually use the ONI in general. So their skill is even lower than the linear method. Yeah, for this one, you can probably go over the notebook too, but what I try to do is, we are predicting also maps of sea surface temperature. I don't want to predict anything inland, because this is data in the ocean. So I created a mask, and then I try to implement the mask here in the network too, and then try to run it. This is gonna take a little bit more to train. But once this is on, we can just see the results here of the prediction. So, just for the last part, to go over this real quick. If you have this open, try to change the runtime to a GPU, and then just hit run all, because it's gonna take a while, up to many sessions. So what I wanted to showcase here is, this is basically a state-of-the-art AI model. So the people behind this, they trained this model with petabyte worth of data, so developed by IBM and NASA, using a vision transformer, which is a fancier method than the ones that we have explored here. It can be used for many different tasks. In this particular case, what I'm trying to look is at downscaling. Downscaling is pretty important, and it's of much interest here in Hawaii, because most of the data that we see do not cover Hawaii or cover Hawaii just as 2 pixels or 3 pixels at most. So downscaling is pretty important to try to have high resolution data in different locations. So this is just most boilerplate too. It's going to try to download a fine-tuned model, which means there is a model that has been trained for one particular task, that is a foundation model, and then they fine-tune, like modify some parameters slightly for a very particular task. In this case, is this one, the downscaling. So, and this model weighs 8 gigabytes, which is why I suggest you run this on Colab, because the Wi-Fi here I don't think is going to hold up. And as this model, there are many different climate emulators right now that you can try to run in your computer. Again, it works on a laptop like this one. It was going to be the fastest, but it worked. So I suggest, if you have the chance to use Google Colab or HPC that has GPU available, try to do so. A single GPU is more than enough to actually run this. If you want to play around with this, so the data that is used, it's called MERA2. So if you download this data for any particular day that you want, you can actually try to run the downscaling here. This example is just using data from 2020, which is, yeah, the model is actually running, no, it's here too. So, yeah. Oh, this one just finished. So this was the input, this is the target, and this is the prediction that the model gave us. It kind of captured a little bit of at least where the values of the anomalies are located, but on intensity, it is not there yet. So this is what I say, like this is one of the problems that you have when you try to apply to global data. We probably try to restrict the region to a more particular location. It would perform way better instead of trying to do global SST. There are tricks to do or to get better results here, but I'm just exploring like the most general or agnostic implementation for a unit here. We go back to this one. Yeah, it's running the inverse. It shouldn't take that long, and then the rest is just visualization. And we can see how these models actually scale the data. So, are there any questions with this part so far? Yeah.
Does that model work well data related to or is it?
I'm sorry?
Is this weather foundational model, is it for the whole globe?
Yeah.
Or could you fine tune it to?
You can fine tune it to Hawaii. So that's why it's called a foundational model, because you can fine tune it for any application that you want, or any particular region you want. So yeah, the result is here. So you can see this is the input, the low resolution. Right now everything looks low resolution here, but yeah, this is the low resolution data. This is the prediction, and this is the ground truth. So it doesn't look. In my screen, I can actually see the pixels here, but in this screen you probably cannot see. It's getting smoothed out. But it's pretty low resolution. Another way to look at it is if we look at the power spectrum. So this is the input. You can see the wave number of the spatial scale solved by the low resolution models is not that good, or what the input is not that good. But when we run this method, it gets real close on the bigger feature, on the larger scale features. But when you go here, like on the fine scale features, it starts getting a little bit weird, and that is being shown here. So this is the difference between the upscale method and the actual ground truth. As you can see, there's not a lot of errors here in Hawaii. So if you want to try to use this method for this particular location, I think it should be. Most of the errors are actually in the continental mid-latitudes in general. So yeah. So play around with this model if you want. Everything is on Google Colab, so just tweak some values, change the dates. You can also restrict the domain here and see how it performs for this particular location. So, yeah. Is there any question with this? Anybody has any doubts?
I haven't read the details, but so the downscaling is a function that's provided by the library?
Oh, the downscaling is provided by the AI foundational model in this case. With IBM, they made like so here we're loading the model. Here, this privy, this is location. This one, Granite Geospatial WXC downscaling. So they fine-tuned for this particular application. So yeah. Okay,
I wonder, at the beginning you mentioned about all this big model from the like Google, other big company, like or I remember the name is Aura. models. Do you think their ability of making prediction has already taken over the classic model, like the work model, and on the classic ones?
Yeah. The prediction skill of these models are actually, it's actually very good. Compared to traditional methods, you start seeing improvements the longer you go on the, because on numerical, on the traditional numerical methods, you start getting instabilities the longer you go on the prediction, prediction time. So there are centers that are using this operationally. The European Center for Weather Forecasting, they have their own suite of AI models because they actually prove useful for this task.
So, I mean, in accuracy, in time span, is all, do they all beat the classic ones? Or
I'll say,
not yet?
I'll say that yeah, they beat them in the long range one. In the short term, well, it's anyone's territory. Sometimes these models are not that good compared to the traditional methods. But for the long range forecast, I think they actually outperform them.
Thank you.
So final. Oh, there was a chat. Oh, yeah. So, if you have some time, please fill the participant survey. It was everything for the workshop. If anybody has any questions, they can just send an email or let me know after I'm done with the workshop. So, thank you.
Thank you.